All right, today we're determining regular annuities. An annuity is a little different from what we were doing before because annuities deal with putting a regular payment in. So Will decides to invest $100 a month. Before, what we were talking about is putting in a set amount of money, say $152, and just leaving it in an account for a certain time frame and letting it accrue interest. This type of account, which is called an annuity, is where you're going to regularly put money into the account. So every single month you're going to put $100 into this account, as well as gain interest on the money that is in the account. So these ones build very quickly, these types of accounts. The variables, A is our total amount, or anyone else know what that could stand for?
Amount of annuity.
Would it be the amount right now or the amount in the
Total
future? No one remembers that. Okay, anyways. So this could also stand for your future value of the annuity. In other words, we're trying to figure out in 30 years how much this will be worth. That's what our A is. It could also stand for a variable FV, which we call our future value. R stands for your regular payments. Okay, so that means the amount you're going to put in that interval. You might actually put it in monthly, daily, weekly, quarterly, semi-annually. It doesn't really matter, but regular payments is what that amount is. Our other variables, which are still our I and our N, we know we have our formulas and how to solve those. Those are going to be the same as before. So let's talk about what we have in this question. William decides to invest $100 a month into a bonds account that is giving an annual interest rate of 5% compounded quarterly. You're going to withdraw the money at the age of 65. How much money will be in the account when you are ready to take the money out? In other words, retire. Okay. So our regular payments are the $100. Okay. And you know what? Actually, we're going to change this question because I didn't realize I'd done this. Just to make this simpler for us, we're going to say that it is compounded monthly. We're going to leave the compound period and the regular payments as the same. Otherwise, we have to do a little more intricate type math, and we'll talk about that after, okay? My fault. I made the question a little too hard. So anyways, they're both going to be monthly. You're going to get 5% compounded monthly, and you're going to invest monthly. Makes the question a little simpler for us. So we have our regular payments. We know I is the interest rate divided by the compound period. What is our compound period in this question?
65? No, 12.
12, that's right. Because it's monthly, our compounding period, C, is going to be the number 12. Okay, so C will be equal to 12. Our R, what does R stand for?
Our rate.
Right. So what is our rate in this one?
0.05.
Yeah, in other words, our 5%. That's going to be our rate. And the other major variable, it doesn't affect the chain, it's fine. Years. We know our compound period is still 12. It's happening every month. Sorry, let's get this color right. There we go. YR stands for years. How many years is this occurring for? Oh, I actually didn't say how old you were, did I?
65.
The reason I used Will is because Will is how old, Will? 16. Okay? So Will is 16. He's going to take this money out at 65. How many years is this going to happen for then?
22.
Subtract. 49 years. Okay? So, for 49 years, money is going to be put into this account every month. Now, it doesn't seem like a lot of money. In fact, many of you guys said you had jobs. You might be able to save that much every month. Let's see how much money, if you actually leave it in there and you have the patience to wait for it, how much money you would actually have at the end. So 49 years is our amount. So we're going to go and put it into this formula here. Our future value, okay, or A, okay, it's the amount. Future value or the amount is equal to our regular payments, which were $100. 1 plus I stands for our interest rate, which is 0.05, divided by the compound period, which is 12 in this case, to the power of N. N is our years, which are 49 times 12. In other words, that's the amount of payments or amount of compounding periods over the course of those 49 years. Subtract the number 1. And everything's going to be divided by our I once again, which is 0.05 divided by 12. Okay? So, this looks a little complex. We got to actually work out this equation here. So, according to BEDMAS, what do we deal with first?
The brackets.
We deal with the brackets first. So, we're going to actually simplify what's inside of these brackets to start this question off. So, it is equal to 100. And we're going to do this all in one step here. We're going to do the division and add the number 1. So, 0.05 divided by 12 gives us this decimal plus 1. We know it's just going to be 1 point, whatever that is. So we get 1.00416. I've rounded this about 5 decimal places. That should be fine. I'm also going to figure out what the exponent is in the process of simplifying. 49 times 12. So exponent of 588. So there are 588 months that are going to pass over this time. Subtract the number 1. And then all divided by... What number will we be dividing by? Anyone know? Yeah, that's right. Because our I is essentially the decimals in front of our 1, that's what we're going to be dividing by, which is our I. Okay? So we simplified that part. Once we've done the brackets, we work with the exponent. So this is going to give us a pretty odd number. We're going to take a look at it. It'll be rather long. 100. And then 1.00416, and you can keep repeating if you like, to the power of 588. Gives us 11.529, blah, 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 blah. 11.5295 is enough. Subtract 1. Okay. And again, all divided by that same term. Whenever we're going through this, guys, always try to think of BEDMAS. How do I get things done? And please recall that these brackets, even this here, this is actually in a larger set of brackets. So now I'm actually going to be dealing with the subtraction next, then the multiplication of the number 100. I forgot to write the divided by, sorry. 0.16. Okay. When we subtract that, that's going to be a little easier to take a look at. We're going to be left with 100 times 10.5295. And then all of that's going to be divided again by a small decimal. Okay. 0.00416. Okay. We're going to subtract, we're going to multiply those numbers. So I subtract by 1 gives me the 10 times 100 equals 1,052.95 and divided by a small decimal. Now, as a side note, when I divide by a small decimal, or when I divide a whole number by a small decimal, does anyone know what the number becomes? Does it become larger or smaller, the number on top? Larger. And the smaller that decimal is, the larger it's going to become. So we're going to divide now by 0.00416. When Will retires, if he's able to just put this in, he'll have $2,531,113 and a quarter. 2.5 million. Is that right?
No. Also, it's a quarter. What's only 5 zeros? Or 5. 1, 2, 3, 4, 5.
5. Oh, sorry, I've written it a little too much. My fault. 2 million. 253,000. My fault. I couldn't see it.
100, sir.
So, if he's able to just put in $100 every month, okay, just a small savings thing, kind of forget about it. By the time he goes to retire, he'll have $253,000